Hello everyone, my name is Sunwoo Kim from KAIST AI. Today, I would like to introduce our work, Feature-Centric Unsupervised Node Representation Learning without Homophily Assumption. I will first present our research background and key research goal. In this work, we aim to learn node representations from the given graph topology and node features without relying on task-specific node labels. An example is shown in the figure below, obtaining representations for nodes A, B, C, and D. Notably, unlike supervised methods, unsupervised node representations can be reused across various downstream tasks without retraining. For example, learned unsupervised node representations can be used for node classification, clustering, regression, to name a few. Then, how can we obtain effective node representations? Typically, graph convolution is widely used to encode given node features and graph topology. Specifically, graph convolution is a process that aggregates neighbor information to update the target node's representation. Consider the left-hand side example where we aim to obtain the representation of node A. For example, graph convolution adds the target node's representation with the neighbor's representation, which is the mean of neighboring nodes' representations. Then, the combined representations serve as node A's updated representation. A key characteristic of graph convolution is that it makes representations of neighboring nodes more similar. Often, neighboring nodes' representation similarity increases after graph convolution than before, as illustrated in the figure below. However, this behavior can be undesirable in some real-world graphs. In particular, many graphs are heterophilic, meaning neighboring nodes often have dissimilar features and belong to different classes, as illustrated in the left-hand side figure. Notable examples include dating networks and fraud networks. In such graphs, graph convolution can make representations overly similar. For example, consider the node feature distribution in the figure below. In such cases, graph convolution can mix the representations of heterophilic neighbors, making the affected nodes harder to classify. Given this challenge, our key question is, how can we control the degree of graph convolution in an unsupervised manner? We now present our key challenge, our breakthrough, and the justification for our solution. Typically, a degree of graph convolution that improves class separability is desirable for downstream tasks like node classification and clustering. For example, consider the left-hand side input feature distribution with the class information. Here, we often aim to learn the degree of graph convolution that yields more well-class separated representations in the embedding space. Unfortunately, in the unsupervised setting, class labels are not given. Therefore, in such cases, it is hard to improve the class separability of representations. Therefore, we need a proxy of class separability. To this end, we use latent class separability as a proxy for class separability. Specifically, latent class separability indicates how well the representations form clusters in the representation space. Consider cluster distribution in the below figure. Here, by improving latent class separability, the embeddings form more distinct clusters as shown in the below figure. Then, how can we know whether the latent class separability can serve as an effective proxy of class separability? To validate this, on real-world graph datasets, we show that under varying degrees of graph convolution usage, class separability and latent class separability show strong correlation. Specifically, we use the following graph convolution function, which consists of input node features, one-hop neighbor-based aggregated node features, and two-hop neighbor-based aggregated node features. In this framework, the three terms are linearly combined using learnable coefficients alpha 0, alpha 1, and alpha 2, each weighting its corresponding term. Intuitively, as alpha 0 has a higher weight, the degree of graph convolution decreases. In contrast, as alpha 1 and 2 have higher weights, the degree of graph convolution increases. As shown in the figure below, across both homophilic graphs, coracizer, and heterophilic graphs, actor and kernel, class separability is strongly correlated with latent class separability. This suggests that, in real-world networks, latent class separability can serve as an effective proxy for class separability. In our paper, we also provide a theoretical analysis of the relationship between class separability and latent class separability. We now present our proposed unsupervised node representation learning method. Based on the aforementioned analysis for class separability and latent class separability, we present our method called FUEL, which stands for Feature-Centric Unsupervised Node Representation Learning Method. In a nutshell, FUEL uses a clustering loss as its training objective. Specifically, we train FUEL to minimize this loss so the representations become increasingly well clustered over the course of training, as illustrated in the figure below. To achieve this, FUEL uses a two-stage framework. In the first stage, FUEL trains a graph convolution model to reduce the clustering loss. Here, the graph convolution model is the one that is used in our analysis. Specifically, the three alpha coefficients are updated to reduce the clustering loss of the node representations, leading to increasingly well-clustered embeddings in the representation space. In the second step, FUEL further reduces the clustering loss using an additional MLP projector. As shown in the left-hand side figure, we adopt an initial residual connection structure and train the projector parameters to minimize the clustering loss. After step 2 training, the representations obtained from this structure serve as the final node representations for the downstream tasks. We now move on to the experiments. We evaluate FUEL in both node classification and clustering tasks. For comparison, we use 15 baseline unsupervised node representation learning methods. We use 14 benchmark graph datasets consisting of 6 homophilic and 8 heterophilic graph datasets. In the node classification task, as shown in the figure below, FUEL achieves the best average rank, demonstrating its strong performance on node classification. Similarly, in the node clustering task, as shown in the figure below, FUEL achieves the best average rank. These results suggest that FUEL shows strong performance in various downstream tasks. Lastly, we also evaluate whether FUEL can effectively control the degree of graph convolution usage. As shown in the figure below, FUEL adaptively controls the degree according to the graph homophily. Specifically, it assigns higher graph convolution weights to homophilic graphs and lower weights to heterophilic graphs. Let me wrap up the presentation. In this work, we aim to learn an adequate degree of graph convolution for node representation learning in an unsupervised setting. To achieve this, we propose FUEL, an unsupervised node representation learning method that improves latent class separability in the learned representations. In node classification and clustering, FUEL achieves the best average rank among the evaluated unsupervised node representation learning methods. Thank you for listening.